Okay, thank you for giving me the opportunity to talk today. Good morning. Let's get started immediately. So often in mathematics, one has some object x, and they want to answer some questions about x. There are some questions which are fairly typical regardless of the particular field of study that you are working on. So X could be a group or a topological space or a knot. But still, often one wants to know if X is trivial. One wants to know invariance of X and questions like this. Today, we are particularly interested in topological spaces. So this is how the previous questions could be stated, especially if one is interested in the homotopy type of a topological space. So for instance, is X contractible? What are the homology groups of X? And so on. Today, I will introduce you to discrete Morse theory, which is a combinatorial tool which can be very helpful in answering these questions when X is given in a combinatorial way. For example, if X is a simplicial complex. Okay, we already know from the previous talk what a simplicial complex is. I just want to mention that we are both interested in the topological picture, which is here on the left. So a simplicial complex consists of many simplices or faces glued together. But we're also interested in the combinatorial side on the right, where we look at a simplicial complex as a poset. It's called the face poset of the simplicial complex, which simply consists of all the simplices ordered by inclusion. And so what discrete Morse theory does is it helps formalize a way to simplify a simplicial complex while maintaining the homotopy type. And the basic ingredient for it is called elementary collapse, which goes back way earlier than when discrete Morse theory was introduced. This goes back to Whitehead, I believe. The idea is very simple. You look for a so-called free face in your simplicial complex, which is any simplex which is contained in exactly one simplex of higher dimension. For example, here, the edge BC is a free face of the triangle ABC. And once you have a free face, you can collapse both these simplices by pushing the smaller one towards the interior of the bigger one. And this preserves the homotopy type, but basically destroys two of the simplices in your complex. So the complex becomes smaller and hopefully easier to understand. As you can easily see, we can go on doing elementary collapses in this example here, at least once more, because there is the vertex B, which is also a free face now. It is a free face of the edge AB. So we can do another elementary collapse. And we end up with a triangle ADC without the interior. So on the combinatorial side, on the right, what we have done is to choose some of the edges of the Hasse diagram of our face poset. So we chose the two red edges. These edges form a matching on our poset because two different edges cannot share the same simplex, because you cannot collapse the same simplex twice. Once it disappears, it's no longer there. So we basically, with some criterion yet to be made clear, we chose some edges forming a matching, and we made all the matched simplices disappear. The question is, what's the combinatorial condition on the matching on this set of red edges, such that there is a valid sequence of elementary collapses that we can perform? And this is answered by the main theorem of discrete Morse theory from about 20 years ago by Forman. He says that the correct condition is that the matching M should be acyclic, which I will explain in a moment. And also, of course, the remaining simplices, also called critical simplices, they should form a subcomplex of your initial simplicial complex X, because every time you do an elementary collapse, a subcomplex remains. So you should leave a subcomplex at the end. What is this acyclicity condition? Imagine to orient all the black edges downwards in our poset, and all the red edges, the ones in the matching, upwards. Then the matching M is acyclic if this graph with the orientation that I just described to you is acyclic. It's not difficult to see that this is the correct condition, because, well, basically this graph is acyclic if and only if there is a total order of the simplices which agrees with this orientation. And once you have a total order of the simplices, you can read it from left to right and do the collapses every time you encounter a simplex which is matched. So when you find a simplex which is matched, it's going to be matched with a simplex which appears later in your total order. And you can collapse both and continue. And it's very easy to see that that this works. So what happens, for example, if we choose a matching which is not acyclic? Do things break down? The answer is, in general, yes. For example, if you take the triangle which was remaining from before, on this triangle we can come up with a matching which leaves only a subcomplex, in fact the empty subcomplex. However, this matching produces a cycle in the Hasse diagram, and this is somehow expected because we cannot deformation retract a triangle or an S1, if you want, onto an empty subcomplex. So this makes sense. With this matching, we couldn't even get started doing our elementary collapses. However, we can still do something with this triangle, because we can imagine to temporarily remove one edge, for example, the edge AC. Then the remaining complex now has three faces, and we can collapse it further. For example, we can collapse the vertex C with CD and D with AD. And what is left is a single vertex. And now we remember that we had removed one edge, and so we reattach it to whatever has remained, which in this case is just a single vertex. So we reattached the edge we had removed to our single vertex A. So what we have done can be formalized in general and leads to a different version of the discrete Morse theory, which can be useful in other cases. Basically, the hypothesis is the same as before. The matching should be acyclic, but we drop the condition that the critical simplices should form a subcomplex. If you look at the picture on the right, this is no longer true. And we obtain a result which is, let's say, weaker, or at least less explicit, because we have that our initial complex X does not deformation retract onto a subcomplex, but rather it is homotopy equivalent to a new complex, X prime, which is not necessarily simplicial anymore, as you can see from this case here. And but the cells of this new complex X prime are in natural bijection with the critical simplices from our complex. So there is a bijection, but the attaching maps are less explicit than before, because here like you cannot easily read everything from the combinatorics of the critical simplices anymore. But still, it can be useful. And a quick word on even more versions of discrete Morse theory, which are out there. So you can actually even start with the CW complex. Your starting complex doesn't need to be simplicial. You can start with an infinite complex. I didn't say it before. I was assuming that X is finite, but you can actually drop this condition by being a little bit careful on what matchings you allow. And there is even a purely algebraic version of discrete Morse theory, where instead of matching and collapsing pairs of simplices, you collapse pairs of generators in your chain complex in consecutive dimensions. And this can be useful, for example, if you want to compute the homology of a simplicial complex or an algebraic chain complex, this is used a lot in practice. Okay. Discrete Morse theory is also deeply linked with a concept which was introduced before that, which is collapsibility. A simplicial complex is collapsible if it admits a sequence of elementary collapses onto a single vertex. And now that we know about discrete Morse theory, there is an equivalent way to say it in terms of the existence of an acyclic matching which only leaves one critical vertex. Okay, why is collapsibility interesting or useful? Because, well, it is stronger than contractibility, but it is more explicit. So contractibility is more difficult to check. I will say a word on this in a moment. Whereas collapsibility is something more concrete that you or your computer can actually explicitly check. Just one important caveat here is that, of course, collapsibility is not equivalent to contractibility. And there are several more or less famous examples in the literature, such as Bing's house or the Dunce hat. These two examples where, strictly speaking, they are not simplicial complexes in these pictures, but you can imagine to triangulate in any way you like to make them actual simplicial complexes. That's okay. And so these two examples, they are both contractible complexes, but they have no free faces. So you cannot even get started with a sequence of elementary collapses. And this is why they're not collapsible. More recently, there have appeared even examples where we triangulate 3 balls and in a way which does not allow any full collapsing sequence. So even when the topology is almost like as simple as it can get, there still can be like the combinatorics of your triangulation, the way the simplicial complex is built, can be sufficiently pathological that you cannot collapse it to a single vertex. So this gives a glimpse on how complex can collapsibility and discrete Morse theory actually be in practice. And this will be the focus of the last 5-10 minutes of this talk. Before that, just one slide going back to our initial questions. Just to mention that, yes, in fact, discrete Morse theory can help answering all these questions. Of course, it's not going to always work, but it can be useful in practice. Do you have any questions? Okay, but your faces are moving, so yeah, I'm confident that you are listening. So let's move to the final part. Let's talk about complexity. So how difficult is it in practice to check if a simplicial complex is collapsible, or to find an optimal sequence of collapses, where optimal means you collapse as much as possible. So you leave as a critical subcomplex which is as small as possible. Well, a preliminary comment when talking about algorithmic questions is that, as I mentioned earlier, contractibility is indeed more difficult, in the sense that in general it is undecidable to determine whether a simplicial complex is contractible or not, at least in dimension 4 and higher. So this is already a good reason to study collapsibility. But what about collapsibility? Well, a little bit of good news is that if you have a 2-dimensional simplicial complex, then you can check if it is collapsible in linear time. And it is actually quite easy to see this. The idea is that you can just collapse every time you have a free face, you just collapse it. And if you ever get stuck, then it was not your fault, but the complex was itself non-collapsible from the very beginning. And why is that? The reason basically is that if once you have collapsed all the 2-dimensional simplices, let's imagine that you did that, whatever 1-dimensional subcomplex you get, a 1-dimensional subcomplex is a graph, and a graph is collapsible if and only if it is contractible. So in whatever way you manage to arrive to a 1-dimensional subcomplex, you can finish collapsing it to a vertex if and only if the initial complex was contractible. So you cannot have made mistakes once you arrive at a 1-dimensional subcomplex. And on the other hand, if you only want to collapse the 2-dimensional simplices, then yes, you can always greedily use any 1-dimensional free face that you find, because 1-dimensional free faces are only good for one 2-dimensional simplex. So you better just use them. So this is the explanation. But even when we ask a slightly more difficult question, this already becomes hard. And the slightly more difficult question is finding an optimal acyclic matching on a two-dimensional complex. So not determining collapsibility, but determining, for instance, what is the smallest set of two-dimensional simplices which you need to keep, and so that this set is as small as possible, and you can collapse all other two-dimensional simplices, basically. And this was known since the 90s. But now, if we go up in dimension by 1, well, it turns out that even collapsibility becomes a hard problem. And this was proved more recently by Tanzer in 2016. So collapsibility is NP-complete for three-dimensional simplicial complexes. And the proof is a reduction from the famous three-satisfiability problem, the first NP-complete problem, we can say. And the reduction requires to construct gadgets associated with the literals in a three-sat formula. I will not go into that in details, but I should mention that not only checking if a three-dimensional simplicial complex is collapsible to a single vertex is NP-complete, also checking if a three-dimensional simplicial complex collapses onto some one-dimensional subcomplex. This is also NP-complete. And in fact, it was proved a couple of years earlier. So to summarize this slide, going from two-dimensional to zero-dimensional is linear time solvable. But going from 3 to 1 or 3 to 0, it's NP-complete. And Tanzer, in his 2016 paper, introduced the general, asked a question about the general decay collapsibility problem. And his question was, okay, what's the complexity status of determining whether a d-dimensional simplicial complex collapses onto some k-dimensional subcomplex for fixed d and k? This does not follow immediately from what we have said in the previous slide. But some cases are already known at this point. There are some simple cases. We have already talked about the 2-0 case, which is greedily solvable. And very similarly, if k is equal to d minus 1, then this is also easily solvable, because if you only need to make the d-dimensional simplices disappear, then you can just use whatever free faces in dimension d minus 1 you have. You just need them for this. So all this diagonal is actually linear time solvable. And we have the two results I talked about in the previous slide. Going from 3 to 0 and from 3 to 1 dimensional complexes is NP-complete. This would be these two boxes over here. And well, it is quite trivial to extend this on the right, because if you have a simplicial complex, you can attach, if you have a d-dimensional simplicial complex, you can attach by a vertex a d plus 1 simplex. And this doesn't really change the problem, but you increase the dimension by 1. So increasing d does not really change anything here. But what about the other boxes? Well, it turns out that about 2-3 years ago, I gave a proof that actually all other boxes are NP-complete. And this proof is based on a different reduction, slightly less trivial one, from dk to d+1 k+1 collapsibility. And this reduction allows you to go in the top right direction instead of just to the right. And this settles the problem in all cases where it was not known before. So it is NP-complete in all non-trivial cases, basically. So my very last slide is about how this polynomial reduction works, because it is actually simple to explain in a few words. So suppose you have a d-dimensional simplicial complex, then you can construct a d+1 dimensional simplicial complex x prime like this. You take many copies of a cone over x, okay, and all these copies share the same base x. So x is in common, and then you have many apices, each of them with its cone, like in the picture here. How many cones do you take? n+1, where n is the number of simplices of x. We're going to see why this number. Okay, now to prove that this is an actual reduction, we need to prove two things. First, if x is dk collapsible, then we need to find a way to collapse x prime to a k+1 dimensional subcomplex. How do we do that? Well, we look at x prime. We collapse the first cone onto its apex, which is something we can always do with a cone. And then we have all remaining cones without the base, and these are up to an empty simplex. These are isomorphic copies of our initial complex x with a one shift in dimension. So we can just copy over our collapsing sequence for x onto each cone without the base. And due to the one shift in dimension, this gives a way to collapse x prime onto a k+1 dimensional subcomplex. Very well. And the final step is, what if on x prime we have a collapsing sequence which leaves a k+1 dimensional subcomplex? So x prime is d+1 k+1 collapsible. Okay, then the idea is that at least one of the cones is collapsed in a way which does not interact with the base. And this is because the base x only has n simplices, but there are n+1 cones. So there are not enough simplices in the base to be matched with the simplices in each of the cones. So now you look at the one of the cones which does not interact with x, and again you can copy over the collapsing sequence in that cone without the base over to x, and there is one shift down in dimension, and this gives you a collapsing sequence for x which only leaves simplices in dimension at most k. And this completes the proof of this reduction. Okay, I think it's time for me to stop. Thank you for listening, and I'm happy to take questions.